Does it, are we recording again?
Yeah.
This is gonna be a little bit choppy.
I don't think it was recording the first time because now the red light's blinking.
It went to green light though. It went from red to
Huh.
green. And
Okay, well, we'll know later on when. All the answers to the test were in the first recording, right? And then, okay. That's a fairly simple thing. So without proving all of them, all right, if A, B, and C are elements of the set of matrices, big M is just the set of matrices, little m and m by n matrices. This is the notation. We have there's an infinite number of matrices that are m by n. Think of, I can put every real number in every position. A, B, and C live in that group of matrices. That's not really complicated, right? We know that we just showed that A plus B equals B plus A. What if I want A plus B plus C? Well, we know this. Think numbers, if you will. I want to add 3 numbers. Can you add 3 numbers simultaneously? It's not a trick question.
Yes.
Yes.
How many numbers can you see at a time?
As you can see.
You have the supercomputer at UCSD. How many numbers can you see at a time? Go see 1 at a time. You can see them at rapid fire, but you can only process, you can't simultaneously process 2 numbers. You can process 1 at a time. Oh, if you can only see 1 at a time, then how many can you add at one time? I had 2 at a time. I can do it fast. I have a computer, I can do it fast. I can still only do 1 at a time because I can only input 1 at a time. I can't simultaneously do multiple inputs. No, so if I'm adding 3 or more things and I'm adding them 1 at a time, does it matter what order I add them in? No. I can add A to B, or I can start by adding B to C, and then that's called associativity. It doesn't matter what order or how you group them. So in other words, we know this from real number addition, don't we? Well, the same thing's true with matrices. Because going back to here, if I put A plus B plus C ij's, I got to group them, but I can change the grouping. So matrix addition pretty easily is associative. If things are commutative, they're going to be associative. If things are associative, though, they're not necessarily commutative, as we see. We will see later. It doesn't automatically go in reverse. Commutativity is actually a tough thing to acquire. Those who've done vector work, right? You've had Calc 3, you've had physics, right? You did a lot of cross products, right? And of course, cross products are commutative, right? No, it's not. A cross B will never equal B cross A unless one was the 0 band. No, it's not commutative. Most things that we're going to do are not commutative, but addition is. And with vectors, addition is the only thing really that is also commutative, and dot product, but that's not a thing right now. Now, with real numbers, think real number for a moment. A plus 0 equals A. A is a real number. Is that a true statement mathematically?
Yes.
Okay. Now I have the matrix of Aij's. We'll call the second one B. And it's the Bij's. Actually, we do like this. And I want it to equal. I want to take my matrix A, add it to a matrix B of the same size, but I want to get back matrix A. Is that even possible? Can you give me a scenario where that would actually work?
Where B would be all
Zero
zeros.
matrix.
If I say Bij is 0, that means every single possible entry into that matrix is a 0. Oh, so if I take matrix A and I add it to a matrix comprised of just zeros, I would get back A. I heard we have a very clever name for that matrix. What do we call it? Well, what do we call it if it's a vector?
Zero matrix.
So we call this the 0 matrix. So in this case, I'd say 0 mn. I need to put the size, because how many 0 matrices do you think there are actually? Was the 2 by 2 matrix of 0? What about the 3 by 2 and the 2 by 3 and the 3 by 3 and the 4 by 3? Please make me, don't make me. Infinitely many. Oh, so I kind of need to mention which one I'm talking about. In calculus, if you mention the 0 vector, does everyone know which vector you're automatically thinking of? So you kind of need to say which dimension you're in. right? So what did we do in calc? We put 0 with a subscript of 2 or 3 or 4. Oh, the 2-dimensional, 3-dimensional, 4-dimensional 0 vector. And we indicated that it was a vector, not the scalar. Well, clearly this has got to be a matrix, not a number. Okay? So there is an additive identity for matrices. Now, one of the things we sometimes forget about algebra is there's two things that go together. Identity and inverse always go hand in hand. So here's the thing. My job in life is I tie shoes. That's what I do. Okay? That's it. Ryan, he's my inverse. Ryan goes around and he unties shoes. He can't help it. So I see your shoes untied, I tie them. Something physically changed. Ryan sees your shoes, he unties them. After we both visited you, what do you notice? The original state.
Yeah.
When a mathematical operation takes place and nothing has changed, that's what is called a mathematical identity. Okay? I physically added a matrix to matrix A and nothing changed. That made it the additive identity. It was a physical thing. I brought my checkbook today. I'm going to write a check to every person here and I'm actually going to sign it. So I wrote you a check for $0 and I handed it to you. So your overall standing did not change. I just did an additive identity, didn't I? But in Ryan and I's cases, that wasn't an identity. We were inverses. Mathematically, an inverse is anything that undoes. So adding an opposite sign undoes. Multiplying by reciprocal undoes. Taking a root when something's an exponent. Doing a log when you use an exponential function. Do an inverse trig when you did a trig. These all undo and get you back to the beginning. So anywhere you have an identity, you'd usually have an inverse. They kind of go hand in hand. And when something changes and something changes it back, that's what it means to be an inverse. So, is it possible that I can take a matrix, add it to matrix B, and get back the 0 matrix? These were all n by n matrices. Is there a matrix out there?
Yeah.
I know what matrix A is. Matrix A is this guy. It's the matrix of AIJs. What matrix would do this? The matrix of every single position is the opposite sign. So there's an additive inverse of matrices. It would be the matrix where every number is the opposite sign. Then when I combine those two, I would get the 0 matrix. Why is this huge? Because right now matrices are acting a lot like real numbers, aren't they? And why is that huge? Because that means some of the conclusions I make about real numbers I might be able to make about matrices. Now, not everything. I can't take a reciprocal of a matrix. No, that's not there. But that's not what we're talking about. Right now we're just doing addition. Okay? With limits, Calc 1. You knew the limit of a sum was the sum of the limits. The limit of a scalar multiple was the scalar multiple of the limit. The limit of a product was the product of the limits. The limit of a quotient, the quotient of the limits. The limit of a function, the function of the limits. Were all those true for derivatives and integrals? Derivative of a product is the product of the derivatives? No, there's a product rule. The integral of a product is the product of the integrals? No, that weren't true. But wait a minute, isn't the derivative of a sum the sum of the derivatives? And isn't the integral of a sum the sum of the integrals? So that one held. How about the scalar multiple? The scalar multiple of the derivative, right? The derivative of k times f of x is also k times the derivative. How about integrals? The integral of k times f prime was k times the integral. So the limit properties that extended, and we're going to do that later on in this class, the limit properties that extended were the sums and scalar multiples. Those are the only ones that extended into other areas. Well, it turns out those are the same ones that we do with vectors in Calc 3. Vector addition and scalar multiplication. Same thing with matrices. Matrix addition and scalar multiplication. So let's define scalar multiplication using the same idea. So if I said, what is Ka? That would be the matrix of K Aij's. Another way of thinking about this, if I multiply a matrix by a scalar, then I'm multiplying every entry of the matrix by that scalar. Okay? That's a very simple thing to do, but it's also a very powerful thing to do. I'm not changing the size of my matrix, I'm just changing the elements, but all of them I'm changing in the same way. The reason this kind of step is really important, sometimes we may be using a matrix that is filled with fractions. Yuck. But if I said, well, let's consider the common multiple of all those denominators, if I multiplied that matrix by that scalar, I'd have a matrix of integers. And as long as I'm keeping track of what I did, undoing it later might be a simple thing. We are going to do a problem next day, it might be the day after, where we're going to look at matrices that are filled with decimal values. Those are really scary. Maybe everything's a 2 decimal place number. Well, what if I multiplied that matrix by 100? Now everything's an integer value. And I might be able to manipulate that one way easier, and then later I can maybe undo it. There's a lot of advantages. So let's start with a really simple, this is just a really simple exercise. Matrix A, let's say, is 2, -3, 1, 4, 5, -6. And matrix B, let's say, is -3, 8, 2, -1, 1, 3. All right? I would like to find 3 times A minus 4 times B. So I want to do two things. I want to do scalar multiples, and I want to do an addition. Tell me about the shape of my result. What do you think it should be? So 2 by 3? If it's not, we're probably in trouble, because where would the extra numbers go? And losing numbers would be just as bad. So this is a simple arithmetic process, but a lot of times we make mistakes because we're doing things in an order that's not really efficient. I cannot do this in one step because I'm doing 2 completely different operations. But I shouldn't take more than 2 steps either, should I? So my first step is not going to be to do the addition of the 2. I'm going to multiply by the scalars. So, what is 3 times A? Go slow. It's 3 times each element. So that would be what?
6 minus 9, 3, 12, 15, -18.
Now what do I want to do? Do I want to do 4 times the next matrix? No. I guarantee if you do 4 times the next one, at most half of you will have the right final answer. Because we're really terrible when it comes to doing things like distributing negatives. How do I know this? Because every group is exactly the same. If I subtract the matrices, you will subtract some of them correctly. The chances that 55 people will do every step correctly, no, ain't gonna happen. Never happened in the history of the world. No. Multiply by -4. To me, that's so obvious and a no-brainer, but most people go, no, I'm multiply 4, then I will subtract all the quantities after you've actually added steps to the problem that will almost ensure there's going to be errors because you have 6 opportunities now to get an error. No, multiply by -4. Oh, then what do I get? 12.
32. 8 of 8. 4. -4. -4.
This is a question on your quiz 2. And I will ask this simple of a question. And as simple as this is, we will not be anywhere close to 100% as a group. Never, I'm not sure we've ever hit 75%. I'm adding single-digit numbers, you're right. But the carelessness of doing so many steps, I want you to not make any errors ever. Well, that's impossible. We'll all make errors, but I want to minimize. So first thing is, multiply by the scalars. And the scalar isn't 4, the scalar is -4 because technically isn't this 3A plus -4B? Because there's actually no such operation as subtraction. That's not a defined operation. Oh, that's really the reason. We have an addition. Now I'm going to combine them. Go slow. 18,
-41.
-41, -5.
16, 11, 30.
Now, one of the things, even going back to baby algebra, okay, I'm going to give you a long list of numbers. I want you to add them up. Regardless of how you do it. Sometimes you rearrange things to get, you like to get 10s, whatever trick you do, but you add it up, you got a number. In stats, I tell people to do every problem twice. If you got the same number, you should feel good. How many have had 119? So, did it always work? You were always told do it twice, which means for most people, how many times did you do it? No, 3. Because the second one is rarely the same as the first one. I laugh. This is every stats class I've ever taught. I say, always do it twice. because you might have just hit a wrong button, right? I have fat thumbs. I don't know why my phone changes my texts, but I know I didn't type that. Every time I hit a T, every single time I hit a T, it puts a 5. Anybody else have that problem? It drives me totally nuts. 100% of the time when I'm typing, I put the, it says 5HE. And I know I didn't hit the 5, but I also have fat thumbs. Okay, right, so I'm talking in stats. We sometimes hit a wrong button. I say in stats, every time you do a calculation, do it twice. If you got the same number, you feel good. And most people, it's laughing, they hardly ever get the same number. So they're just praying that the third time they do it, they get one of the first two. And that doesn't always work either. And it's kind of laughable. But there is no check, is there? When you're simplifying a quantity, there is no check. There's only a check when you're solving. You take your solution, you substitute it back in and see if it works. We're simplifying something. There is no check. You just got to be careful. And that means it's virtually impossible to spot an error, right? So you just go slow and, double check. That's a simple thing. Nothing complicated about this whatsoever. Right? This is the basic manipulation, not a whole lot. Now I'm going to define a couple of terms. They're kind of cool. A very useful term. The transpose of a matrix. Okay? The transpose of a matrix, and we indicate it like this. AT. Now, first of all, AT, remember my original A. Sorry, this would be 1 N, this would be M, sorry. And, hold on. Oh, sorry. Yeah, these were the original entries. And then this would be MN. I got everything backwards, don't I? No. This was row 1 of A. This was row 2 of A. Does that make sense? This was row M of A. I've switched the order of the rows and columns, which means that this is the matrix of A, J, I's. Keep it real simple. What's B transpose? It's that simple. There's no algebra taking place. The row of the first one became the column of the second. And the column of the first one became the row of the second one. That's what a transpose is. So an M by N becomes an N by M. It's simple. You swap positions. Now, does anything stay the same? Yes, the 1, 1, the 2, 2, the 3, 3, and so on stay the same because I'm not changing any numbers there. Good question.
Sorry, underneath AT, is that a parentheses or just another bracket? Sorry.
If A is the matrix of AIJs, this is I'm switching row and column. That's all that means. Transpose is a very, very useful tool. We're going to come up with an extremely powerful formula in a couple of days. One of the coolest things, those who've had statistics, you remember doing least squares regression lines and things like that, and you had this massive set of formulas. There were so many calculations and stuff. That formula comes from linear algebra. It comes from matrices. I'm going to show you where it came from. And you're going to take every problem you ever did and do it in a fraction of the time because we're going to use matrices to do it. And it's extremely cool. It's extremely powerful. But it involves transposes and other things. I think that is going to be a week from today. Because I think there's 2 things in section 2.5. I think that was the second of the 2. So I think I'm doing it the following Tuesday. I'll have to look and see. Okay, so that a transpose is a nice thing. So now what we need to do is we need to define matrix multiplication. This is huge. So the first thing I want to point out, I'm going to define something called a column matrix. This is an n by 1 matrix. There's only one column, n rows. That's why we call it a column matrix, because it's a matrix of literally one column. This is a vector. I'll just for fun call it, oh no, vector A. It's a vector with n entries. The first one was a column matrix. The second one is a vector. Of all of the things you'll ever learn in your life mathematically, this is actually, I don't want to say it's the most important. It's probably going to be the most commonly used and certainly the most useful. A column matrix is isomorphic to a vector. So we treat a column matrix and a vector as absolutely identical objects. We treat them as exactly the same thing. You didn't see that one come, did you? A column matrix, and by the way, before we're done today, you're going to see why we do that. It actually is the same thing, a column matrix. So which one do I use? It's a context thing. If I'm using matrices, I'm going to use the column matrix. If I'm using vectors, I'm going to use the vector. A row matrix, one row, is not a vector. Only the column matrix, and you're going to see why really, really shortly. So now that I've defined the column matrix, I can define a matrix multiplication. Okay, so A is going to be that guy, A11 down to AN1. I'm going to define matrix B to be B11, B12, down to B1n. I have a row matrix. I have a column matrix. I am going to define the product. Okay, definitions you like, because you can't question the definition. Okay, what month were you born?
February.
February. Well, why February? Because that's when you were born. Can I question February? What's your area code?
Mine?
You're 619-858, what are you?
619.
Why? Because that's what the phone company gave you. It's a definition, in other words. I can't question that. I can question math. You cannot question a definition. When you look up a word in the dictionary, you say, well, why is that the word? Why can't it be this? No, it's a definition. We love definitions. It's an absolute, unquestionable. It's one of the building blocks. We are going to define this, which is where you see the 3 bars. You have used this before. If you've been in my classes, you've seen multiple uses of this. This means it's defined to be the following. It's a 1-by-1 matrix. It's a 1-by-1 matrix. That's kind of boring. It's A11, B11 plus A21, B12 plus all the way down to AN1, oops, AN1, B1n. Basically, it's this product plus this, plus this, plus this, plus this, plus this, until I get down to the end. You notice I had to have the same number. So the n by 1, the 1 by n. If I had 3 numbers in this column, then I have to have exactly 3 numbers in that row, or I can't perform it. It would be incompatible. This is the definition of how I multiply a column matrix by a row. I have to start with this to take bigger things, but this is how we do it. Matrix multiplication is you always take a column, you multiply it by a row, and you get exactly 1 number in the end, and that number is that big humongous sum. Everybody okay with that so far? So now, let's say I have matrix A, and that's m by n. I have matrix B, and that's n by p. Let's assume that m, n, and p are all different numbers. So the first one is 3 by 5, the second one's 5 by 7. But they both have an n right there adjacent to each other. I'm going to get, we'll call it matrix C. First thing is C is going to be m by p. And the matrix ofCij's, like we said before, all I need to know is what does the ijth entry look like? You're going to like this. We're going to do several examples. This is going to be simple. This part looks complicated, but it's the only way we can define it. There's no simple way to define this other than what I'm going to do right here. This has to be the same. What is n? N is the number of columns. Here, n is the number of rows. If they're not the same, then I will run out of one before I run out of the other. That's kind of important. The ijth entry here is the sum I'm not using a K so far. We'll figure out what K has to be in a moment. And it's the AIK times BKJ, where K is going from 1 to N. In simple English, okay, you know what, I just realized, I wrote this backwards. My bad. I wrote this back. This should be, I'm sorry, this should be B times A. I'm looking at it going, oops. It's the row times the column. I'm gonna take this, so that was almost a disaster. Actually, let me write it. This is A, this is B. This is the ith row. This is the jth column. So this is A, I1, I2, I3, I4, I5, I6, right? That's the ith row, or excuse me, the jth row. Over here it's B, 1J, 2J, 3J, 4J, 5J. That's the jth column. They have to have the same number of entries. And we're going to do it in a moment. And I go boom, 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 boom. And that's the ijth entry of the product. It seems kind of complicated, doesn't it? Now, having said that, if I do the ith row of A times the jth row of B, will that be the same as the ith row of B times the jth row of A? Or jth column of A? No. There's no possibility. Matrix multiplication is not commutative. In fact, most of the time, if you try to commute, it can't actually be done. See, if I try to commute these two, it's impossible because that middle number won't be the same number. So matrix multiplication is simply not commutative because rows and columns will not add up. The row of one times the column of the other will not be the column of one times the row of the other. Not generally. There are a handful of exceptions. For example, if one of these is the zero matrix, if they are the same matrix, there's a few scenarios but it's really, really special cases. In general, it's not commutative. Okay, so let's do a really simple example because this is something you're going to do often and it should never, ever give you problems. All right, let's say that matrix A, can't believe I actually said that backwards over there. Let's say matrix A is 2, -3, 4, 6, 5, -1. And let's say matrix B is, how about 2, 1, 0, 4, -1, 3, -2, 5, and 2, -1, 3, 6. Okay? A is 2 by 3, B is 3 by 4. Can I do A times B? Yes. Can I do B times A?
No.
No. B times A would be a D and E. It's not just that I'm not going to get the same answer. More often than not, you won't even be able to do the multiplication if you try it in reverse. So I want to do A times B. I'll put it up here so you can see it. Now, what's the shape of A times B going to be? 2 by 4. Okay, follow along with me. I want this to be really, really simple. I'm going to take the first row of A, I'm going to multiply it by the first column of B, and that will be the 1, 1 entry in my product. Okay? 4 plus 3 plus 8. So 15? Now, I'm going to take the first row of A and multiply it by the second column of B, and that will be the first row, second column of my product. All right? 2, -9, -4, I think that's -11. And I'm going to keep going. 0 plus 6 plus 12, 18. And then finally, first row times fourth column, 8 minus 15 plus 24. What's that? 17. I've now finished the first row of the product. So now what do I want to do? You take the second row. And do the same thing. 12 minus 5 minus 2. That'll be a 5. 6 plus 15 plus 1. 0 minus 10 minus 3. And finally, 24 plus 25 minus 6. This is how you multiply two matrices. So the first thing, the matrix multiplication has to be defined. So your rows and columns have to match. That's actually quite critical. Okay? It's the row of the first one times the column of the second one, and so on. That's just not that terrible, is it? Now, we're not even talking about solving it yet. We're just trying to say, how do I actually do it? So this leads to the first humongous change. A1n xn. There you go. I have m equations in n variables. They don't have to be the same. I mean, we like it when they're, but they don't have to be the same. So if m and n are bigger than 2, we're probably using a matrix. It would be totally inefficient to do this algebraically. So we would do row operations on the first matrix and do all, on the coefficient matrix and or augmented, whatever. I want to change something entirely here. Okay, I'm going to be really lazy. Okay, there's my coefficient matrix. There's a column matrix of the x values. If I perform this multiplication, won't I get a11x1 plus a12x2 plus a13x3, blah, blah, blah? Won't I get exactly that line? Does that make sense? And if I perform the next row, the next row, the next row, won't I get exactly the system of equations, but sitting inside of a matrix? So therefore, what must this equal? This must equal this, because I'd have a matrix with this on the inside equaling a matrix with this on the inside. Oh, because remember, when I perform the operations, this was, that's one entry. That's just one entry of the matrix, and it would be that guy. I have just written my system of equations as a matrix product. Not only can this always be done, this is actually what we're going to be doing most of the time from now on. Call this matrix A. Call this matrix X, and call the last matrix B. What have I got here? This is my system of equations. The coefficient matrix A multiplied by the column matrix called X equals the column matrix called B. But in the end, what is my goal in the end? My goal in the end is to find these values. So my goal in the end is to find this matrix. And I'll say my matrix X equals the following, which means I won't be writing my answer as a column matrix. I probably want to add as a vector. Remember what I said last day? I said right now we're giving terminal points. We're giving the point in space, but the terminal point of a vector is the same thing. Well, even if I had never done a row operation, this is still correct, this is still valid. And the representation of my answer, my goal is to say x equals. And I could do it as a column matrix, or I could do it as a vector, which means we're not going to give ordered n tuples anymore as solutions. We're going to actually give vectors as solutions. And that will open up a whole world for us. And here's the reason. Because that is, every system of equations that exists, you can do this too. Can I easily solve this? Well, it might have a unique solution. It might be inconsistent. It might be a dependent system that has to be parameterized. I don't know. I mean, it depends on the specific problem, but this is always true. Our goal is then to solve for the x. Now, what if this guy here, m and n are equal? I don't know, did I define that yet? If m and n are the same, we call that a square matrix. Did we talk about that on day one? A square matrix is 2 by 2, 3 by 3, 4 by 4. Same number of rows as columns. That's huge. Because if I'm starting with a square coefficient matrix, there's a whole bunch of things I might be able to do. Whole bunch of things. Okay? Okay, a square coefficient matrix. Well, if my matrix A actually, I'll put one more here. Okay, I got a square matrix. I have n by n. More often than not, we're going to deal with square matrices because they just have so many properties that non-square ones don't have. That is called the main diagonal. You don't really talk about diagonals if it's not square. That's called the main diagonal. Why do I call it the main diagonal? Well, when we did row operations, right, we put zeros below, then we worked our way down. Each of those little matrices were called minors, and each of those have their own diagonal. But it wouldn't mean the main diagonal, because that's the one for the existing matrix. As I whittle my way down, you know, this is 10 by 10, then I'm eventually going to have 9 by 9, and 8 by 8, and 7 by 7. Each one of those will have their own individual diagonals. The diagonals start in the upper left and in the lower right corner. Okay? So there's a lot of information in that matrix right there. Excuse me. So here's sort of the next thing. Okay? Let's go back to baby algebra for a moment. I want to solve a times x equals b. Let's assume that a and b are not 0. Well, we know we're to multiply both sides by the reciprocal, and that's our answer, right? If I multiply both sides by the reciprocal, I would get this, correct? Just for the heck of it, isn't the reciprocal of a number the same as that number raised to the negative first power? Isn't that true? It's impractical, but you remember when you were doing exponents in baby algebra, you might have quotients of things with positive and negative exponents, and you went over all the rules of exponents to simplify it. But is this statement still true right here? And a to the negative first power times a, isn't that 1? Mm-hmm. So therefore, I still get that. Life is good. It's the 1 that I'm interested in. Does a matrix potentially have a situation where you could, is there a matrix that acts like a 1? Huh. Is there a matrix that acts like a 1? Let me start with matrix A. I'm going to make it 2 by 3. 2, negative 1, 3, 0, 4, negative 5. Let me call matrix B, how about, excuse me, 1, 0, 0, 0, 1, 0, 0, 0, 1. And let me call matrix C 1, 0, 0, 1. I would like to erase this. I would like to perform the following multiplications. A is 2 by 3, B is 3 by 3, so I can do A, B, correct?
Yes.
Can I do A times C? No, but can I do C times A? Yes. Very specifically, I wanted my A not to be squared. Well, 2 by 3 times 3 by 3 should be 2 by 3. And 2 by 2 times 2 by 3 should still be also 2 by 3. Okay, so let's do this. So I have 2 plus 0 plus 0, okay? I have 0 plus negative 1 plus 0, okay? I have 0 plus 0 plus 3, okay? 0 plus 0 plus 0, okay? Probably should make it closer. 0 plus 4 plus 0, okay? And 0 plus 0 plus negative 5, okay. Crazy stuff. All right, now over here, I'm going row column, so and then what will I get next? I'm doing C first, so that row, and then times the second column, and then times the third column, and then I'm gonna go that row times the first column, and then times the second one, and well, that's weird, I got the same thing. Oh, these answers ended up being the same. In fact, these answers didn't just end up being the same, they both ended up being A. That's interesting. I performed a matrix multiplication, one on the left, one on the right. I had to use compatible. But I did it with those very specific matrices. In a sense, did those matrices act like the number 1 does to regular multiplication? Yes. And we call 1 the multiplicative identity. So we call both of these identity matrices. And we actually label this one, this is so clever, I3, I2. First thing is an identity matrix has to be square. It cannot be anything other than a square. And the subscript just refers to, is it 2 by 2, 3 by 3, 4 by 4? So when I multiplied A on the, what did I do? I did A on the right, and on the other one I did C on the left. So I got A times B, C times A because of the compatibility, and in both cases I got back A. This is an absolute. When you do a compatible multiplication, that means it's got to be the right size. If you multiply a matrix by an identity, it doesn't matter which side you multiply it on, you get back the original matrix. Absolutely always. And I said to you earlier, mathematically, anywhere you see an identity, what goes along with it? The other I word? There's always an inverse. If there's an identity, there has to be an inverse. Identity leaves it unchanged, inverse undoes. Huh. So perhaps there might be such a way that I can multiply two matrices together and actually get the identity. See, if I multiply a number by its reciprocal, don't I always get a 1? If I add a number to its additive inverse, don't I always get 0? When you combine something with its inverse, whatever that operation is, you generally get the identity for that operation. 0 is the additive identity, 1 is the multiplicative identity. So is it possible there's a matrix version of this? Yes. But there's a few very specific rules. It is possible to find the inverse of a matrix, but first of all, the matrix has to be square. It absolutely has to be square. Meaning, if A is n by n and A inverse exists, there is no guarantee, and we're going to figure out what is required to make it exist over the next 2 days. But if A inverse exists, then two things. A times A inverse will equal A inverse times A. This is one of the only times matrix multiplication has to be commutative. Because if a matrix is multiplied by its inverse, you will get back the identity. And it doesn't matter which order the old multiplication is. If it's an inverse, okay, that's an absolute. If it exists, we don't know if it exists yet. So we're going to look at how to find one over the next 2 days, today and next day. Today we're going to do the easy ones, next day the more complicated ones. Boy, this is kind of tricky. All right, so for n by n A, so we say that A inverse exists if and only if A is, I'm introducing a new word for you, non-singular. Okay. This definition almost feels kind of backward. Because doesn't singular sound like a positive thing and non-singular sounds like a negative thing? And I want the inverse to exist. Doesn't that seem a little bit weird? Well, it's what the word singular means. Doesn't mean what it means in the English language. It means something very, 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 very different. And we're going to go over this. Again, we're going to spend a lot of time on this. The sun, any star out there, right? Huge mass, huge volume, very low density, right? It's gas. You can't change the mass of a star, but what if you made the volume less? Then you'd make it more dense, wouldn't you? Keep making the volume smaller, making it more dense. Okay, I'm assuming all of you have had some level of physics. Okay, everybody here emits a gravitational pull. Did you know that? How do I know that? Because you all have
Mass.
mass. It's very important. So I'm going for a run today, and Natasha decides to turn on the gravity. Does that mean I'm going to make a beeline for?
No.
No, I can't approach her unless I was already headed toward her. But what can she do? She can alter my path, right? Change the direction of my acceleration. We go through a lot of this, especially if you were in my Calc 3, we talk about this. You can alter my path because of the gravitational pull. But you'll do more damage if I come closer, won't you? In fact, gravity, or the gravitational pull, if you will, is influenced by really three things. My mass, your mass, and the distance. Oh, and it's actually an inverse square relation. So you double the distance, 1/4 the pull. Cut the distance in half, 4 times the pull. Now think of this, that star has shrunk in size so things can get closer without getting burned up. It's shrinking and shrinking, the star dies. It's shrinking and it's shrinking and it's shrinking. Is it losing any mass, by the way? No, but what's happening to the density?
It's going up.
It's going up. What's happening to the gravitational pull? It's going up because things can get closer and closer and closer and closer. And in fact, eventually that star dies. It's in theory only, it's literally shrinking into one point in space, which would now have infinite gravitational pull.
Black hole.
That's what the definition of a black hole is. And it's also called a singularity. The word singular means you are trying to divide by 0. That's literally what singular in English means, one of something. In math or physics, it means you're trying to divide by 0. That's why it's called a singularity. It's not equal to 0, but it's approaching 0. What's approaching 0? The actual volume. Does it get to 1 point? No. And remember, it's all in theory. You know, it's not like we can, drive to the black hole, study it, take pictures, and come back home.
Doesn't look like that.
But it's such cool science to understand and discuss. So the term singular, that's bad to be singular. It means your denominator is looking like a 0. So if a matrix is singular, it's not a nice matrix. We don't play with those matrices. We don't invite them over. Okay? When you're picking people on the kickball team, right? There's the girl with the broken leg in the cast, and there's the singularity. You're picking the girl with the broken leg in the cast, right? You guys ever see Megamind?
No.
I like to get down to the last 2 goalies, and he's picked last. They always have the girl because she's got a cast broken leg. They pick her before him because he's that bad. And I'm thinking that playing goalie with a cast and crutches is probably not easy, but
Not a good idea.
So in matrix world, we're going to look at this only for a 2x2 today because a 2x2 is special. A 2x2 is the only matrix we can find the inverse immediately with doing very, very little work, because I want to do this so we understand what's going on. Next day we're going to do it in general for bigger problems, because there's now a whole series of steps we have to do, and it's not a short problem. But it's absolutely critical that we know how to do it. All right, so let me go to let's do the following. All right, here we go. I've got so I want to get the simplest one. Got AX plus BY, and let's see, how do I want to? Oh, actually, you know what? I'm gonna do it simpler. I'm sorry. I'm gonna do it a simpler way. Okay. I'm gonna take a matrix A, B, C, D. There's my matrix. We'll call that matrix A. We're going to make one assumption. We're going to assume the inverse actually exists. And this will be more clear with next day's lecture. Here's the extremes of the spectrum. You have your matrix A. In the middle, you have your identity matrix. And the other extreme is A inverse. I'm going to perform legal row operations on A until make it look like the identity matrix. If an inverse exists, I can do this. If the inverse doesn't exist, then I cannot do this. This is how I know it exists. If I can make A look like the identity matrix. If I perform the exact same operations on the identity matrix at the same time, it will become the inverse. And the way row operations work, the way a row operation is even legal is any row operation I do, there's always a path backwards. So if I multiply by a scalar, I multiply by its reciprocal. If I take a multiple of one row and add it to another, then I take the opposite multiple and add it to the other. If I do a row switch, I switch them back. Those are the only three things you can do, and all three could be undone. So I'm going to take a simple matrix, do row operations so it looks like the identity. And so how do I do that? And this is what we're also going to do next day. I do that by augmenting this with the identity matrix. And a lot of times the textbooks will do this, just so keep you mentally. So we write it like this. We say A augmented with I. And it's got to be the right sized I. So I'm going to do it for 2 by 2 and a 2 by 2 only. There are multiple paths that will get me here. This is the first one. We'll see things as we go, but we don't have a ton of tools yet. Okay? Well, what do I want to do first? Well, A is my pivot. So maybe the easiest thing, rather than put fractions, maybe just multiply the second row by A. You like that one? Or I can multiply the first row by 1 over A. I think you'd rather multiply the second row by A. Okay, so I'm going to do A times row 2. So I have A, B, 1, 0. I have AC, AD, 0, A. Now let's take negative C row 1s and let's add it to row 2. Okay? When I do that, I'm going to have A, B, 1, 0. Negative C of these, there's my 0. Negative C of these, that would be AD minus BC, would it not? Negative C of these, and then A. Well, I can multiply it through by the reciprocal, but that's going to make that really, really nasty if I did that, wouldn't it? So maybe I'll just multiply this row by AD minus BC. AD minus BC is a number, by the way. It's not a combination of things. So what if I just said, let's multiply first row by this number and do the exact same thing? Then I don't have to worry about fractions. So let's take, let's go AD minus BC times row 1. So now I have A times AD minus BC. I have B times AD minus BC. I have AD minus BC, and in the last position I would have a 0. Yikes. 0, AD minus BC, negative C, A. All right, so now I want to take negative B of these and add it to here. And then I'll have my 0. Then I'm basically one step away from being done. So negative B row 2s plus row 1. All right, so I have A times AD minus BC. Make sure that's what I still have, right? Yeah, okay. A times AD minus BC, and then I'm going to do negative B of these added to here. That would be a 0. Negative B of these. Wouldn't negative B of these be positive BC? And those BCs would cancel, wouldn't they? So what would that leave me on top? AD. Does everyone see that? I'd have AD on top. And then lastly, I have negative B of these, plus that would be negative AB. And here I have 0, and here I have AD minus BC. Here I have negative C, here I have A. I'm almost done. Here was our goal, and this is, by the way, what I'm doing here, we're gonna do so many times in this course for various reasons. We're gonna do row operations until the left side looks like the identity, in which case the right side will be A inverse, and I'm gonna show you that in a moment. The left side's not quite the identity, but I do have the zeros in the correct places, don't I? So I need that to be a 1, I need that to be a 1, and then I'll be all finished. So I'm gonna multiply row 1 by the reciprocal of this number. I'm gonna multiply row 2 by the reciprocal of this number. Then what I get on the right is my inverse. And by the way, this will give us a tremendous shortcut. So 1 over A times AD minus BC row 1, and 1 over AD minus BC row 2. So now I got 1, 0, 0, 1. That's awesome. When I do this, the A's will cancel, won't they? Did everyone see that? When I do this, the A's will cancel, and I'll have what? D over AD minus BC. When I do it to this, the A's will cancel, and I'll have negative B over AD minus BC. When I do this to this, I'm going to have negative C over AD minus BC. And when I do it to this, I'll have A over AD minus BC. This is our inverse. It looks kind of scary, but it's not totally scary. So that means, I'll put it up here, my A inverse is D over AD minus BC, negative C over AD minus BC, negative B over AD minus BC, and A over AD minus BC. And I think you all see something they all have in common. They have the same denominator. But the denominator is just a number. Could I pull that out of the matrix?
Yeah.
Remember, scalar multiplication means you take the same number multiplied by every entry. That means I should be able to go in reverse. If I took a matrix and multiply every single number by 2, shouldn't I be able to factor a 2 out of that matrix in reverse? Huh. So what if I wrote it like this? Remember what my original matrix looked like? It was A, B, C, D. My new matrix is simply a multiple. It's the same 4 numbers, just kind of rearranged, isn't it? Now, I said, if the inverse exists, then this is what it is. Well, when will this inverse exist? This is pretty easy. As long as what?
That's not 0.
That's not 0. Because if that is 0, the inverse won't exist, but also what does it mean? It means I'm trying to have a 0 in the denominator. That makes it a singularity. That's where the singularity comes from. I would have a 0 in the denominator, that matrix won't exist. So as long as that's not 0, I'm good to go. So that means if I gave you the original matrix, you could tell me the inverse almost instantaneously. Whoa, that's cool. This matrix right here, involves something that I'm going to introduce much later in the course. But it involves, well, actually not much later in the course, a couple weeks. Something called a cofactor matrix. Every square matrix has a cofactor matrix. This has to do with the cofactor matrix. And that's not important today, but we're going to use that fairly soon. I think it's 2 weeks from Thursday. I think that's the lecture will come at you. So let's do a really simple problem. I've got a matrix A. Let's say it's 3, negative 4, 2, 1. Keep it real simple. I'd like to know what A inverse is. Well, let's start by doing AD minus BC. What would that be? It would be 3 minus negative 8. What's 3 minus negative 8? 11, good, okay, and we did that without a calculator, awesome. So they're at 1/11, because it's 1 over, and then what I'm gonna do is do my rearrangements. You notice A and D flip, and B and C change signs. There's my inverse. That wasn't very hard, was it? Might I, question?
How do we get the 1/11 again?
That part. So that minus that was 11. So 1/11 is what goes in front. Now, I'm pretty sure that's the right answer. You okay with that? Pretty sure. Might have made a mistake someone, but pretty sure that's right. Can I know for certain? How? Multiply it out. What do I mean? Multiply by A. All right, let's see. 3/11 plus 8/11, that's 11, that's 1. 12/11 minus 12/11, that's 0. 2/11 minus 2/11, that's 0. And 8 plus 3/11 is 1. Is my product the identity matrix? Right. Minor rejoicing, we kind of expected it, but absolutely without exception, you have to multiply it out every time. Oh my gosh. This process is so simple, but if I drop the negative, what kind of knucklehead mistake might I make here? Do you suppose if I'd asked you guys to do it and then write your answers on a piece of paper and turn it in, we have 50 plus people here, do you think all of us got 11? Do you think some of us might have gotten something else because we made a boo-boo? Yeah, we're never going to be 100%. You got to check it. What if I multiplied it out and I didn't get the identity? Well, that means I got an error. When I'm manipulating, I have the negative in the wrong place, or I forgot to put a negative. I will never know unless I check, but the check is so fast, so fast. And I'm going to show you now an even easier check. You didn't like the 11s, did you? 3 plus 8 is 11. 12 minus 12 is 0. 2 minus 2 is 0. 8 plus 3 is 11. Just so you know, I never use this first. I'm lazy. Are you kidding me? I'm proud of it. I rip open my sheet. I have the big L on my chest with the cape and everything. No, not that L. The lazy L.
Oh.
Yeah, I know what you're thinking. Okay. Yeah, I never multiply the fractions. I multiply this and then do the fractions at the end. Always, without exception. Because I need to know that I'm right. The process is simple, but you're going to make mistakes occasionally. It's unavoidable. Okay? If a matrix is singular, we're not dead in the water, but it makes it hard to work with when I'm solving things because, I can't do an inverse. But, here's the thing. You're going to like this. This is where we're going, and this is the first really cool result. All right, let me use exactly that problem. Here's my problem. I have 3x1 minus 4x2, I don't know, equals 7. Let me just make up numbers. I have 2x1 plus x2 equals negative 5. I am absolutely money back guaranteeing you that this has a unique solution. Because the coefficient matrix is non-singular, there is a set of conditions that we're going to develop over the length of this course. They're called the equivalent conditions. By the end, there's probably 10 of them. If one of them is true, all of them are true. And when you're trying to prove something, you're like, I don't have this, but I have this over here. If one of them is true, they're all true. And we're going to be proving that. And therefore, I can make monumental, humongous conclusions using things that weren't even necessarily what I was looking at because all of these conditions hold. So first rule of thumb, AX equals B, that one I said, has a unique solution if and only if A is non-singular. That's one of the first, and a lot of people would say really important conclusions. Well, solving systems, though, isn't what we're going to do all semester. But that system has a solution if and only if the coefficient matrix is non-singular. Because if it's non-singular, then the inverse exists. And the solution to this is this, because I multiplied both sides on the left by A inverse. I got an identity on the left. Let's do that for this problem right here, just to illustrate what it is we just did. You'll like this. It's kind of cool. All right, so if I write this as a matrix product, and this is one of the reasons you would write something as a matrix product, because you planned on using the inverse instead of row operations. Okay, so that's A, that's X, that's B, if you will. We just figured out what A inverse looks like. There's A inverse. So I can say with absolute certainty by the way, you always multiply it out. You don't leave the fraction in front when you're stating the matrix. Okay? Let's multiply this out. 7 minus 20, that's negative 13 elevenths. There's no disadvantage right now using fractions. Negative 14 minus 15, that's negative 29 elevenths. I am finished. There's my answer. So in other words, what's the value of x1? That. What's the value of x2? That. Can we check this easily enough? Yeah, let's go back to the original equation. The nice thing is, if it checks in one, it has to check in all. If it doesn't check in one, then it will fail in all. Because I did not use any of the rows specifically to get any of the variables. When you're doing row operations and you made a mistake along the way, and you go to that last one, and your bad answer is always going to work on that first equation. It's not going to work on any of the other ones. But this one is an all or nothing every time. So let's check. And you can use your calculator. So negative 39 plus 116, that is positive 77 elevenths. Catch that? Lazy. Next one. Negative 26. Where am I? I'm sorry. Where are we? Negative. Oh, negative 26 plus negative 29, that's negative 55 elevenths. Does that work? Yeah. Using your fraction K on your graphing calculator, piece of cake. So I'm done. So therefore, what would be the most efficient way to state my answer? Well, since my problem didn't start as a matrix, I just said here's a system of equations, then probably the answer most people would give is this one. So technically, it would be the terminal point of that vector would be the solution to this. But from this point on, by the way, the homework you're turning in on Thursday, I still want ordered n tuples because there's no vectors yet. This is quiz 2 stuff. So what you did was fine. You don't need to change things to vectors yet. But this solution here is the same as if I gave you an ordered pair saying it's the terminal point of this vector, right? Because that vector starts at the origin and stops at that point, okay? But I just solved the system of equations not doing a single matrix operation. I did not do the addition method. I didn't do substitution. It turns out, going back to baby algebra, let's do 2 variables and 2 unknowns because we could also include graphing, couldn't we? That was the first technique you learned, and it only worked if your numbers were small and integers. But that's the first one because you can visualize it. It was easy to see. But that wouldn't have worked for this one, would it? Fractions. So you learned how to solve graphing. You learned how to do it substituting. That's solving for one variable, substitute, or the addition, taking multiples of your equations and adding them to it. So sometimes it's called elimination by addition. You then learn a matrix approach, row operations. This is completely different. We now learn to do it using matrix multiplication and an inverse. There's actually one more, and we're going to do this at the end of chapter 3. And a lot of you remember this from baby algebra. You remember Cramer's rule.
Oh, yeah.
That involved determinants, which is absolutely different from everything we've done. There's exactly 6 ways to solve a system if it's 2 by 2. If it's bigger than 2, we throw out the graphing, because unless you have like a holographic image to create your planes, you're probably not graphing. But the other 5 are still valid. But if you have more than 2 variables, you're probably not doing substitution in addition. So you're probably sticking with a matrix or inverse or the other one. So, and those are all learned in this class and developed. The ones you can use remedial algebra for are fine, but they're probably limited to 2 variable problems. Okay, that's why we start small in this class and we build up. Any question on this? Okay, this is the intro to this. We're gonna finish this concept next day. We're gonna find the inverse of a 3x3 or bigger. It's very different than this. This was a piece of cake because a 2x2, this is one that you might want to tattoo on your arm because it's so useful, it's so convenient, and it comes up fairly often. Use the washable ink, you know. It's kind of, don't have your
I
ex-girlfriend
have a
tattooed on
Sharpie.
your arm. It just, yeah, it's not cool.
Just use a Sharpie.
Use a Sharpie. All right, guys, go ahead and press the button. We'll stop. And I'm hoping and praying the top